Okay, so welcome again. We discuss a new lecture again today, lecture number 23. So before we get into this lecture, let's recap the last lecture. So in the last lecture we discussed the microstructure evolution. In isomorphous system. And basically binary copper nickel alloy. So we looked at the microstructure under both equilibrium and non-equilibrium condition. So under equilibrium condition, your microstructure goes from 100% liquid to, this is above liquidus, to an intermediate state between liquidus and solidus, where you have this chunks of alpha phase so this is alpha phase and this is liquid phase. So alpha of composition, some intermediate alpha of composition typically higher than the, so it will be xc greater than c naught, and this will be typically c less than c naught. Okay, and finally, so this is between liquidus and solidus, and finally below solidus we will have completely alpha phase. So this is alpha, 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 alpha. These are grains of alpha separated by the grain boundaries, and this alpha will be of composition C is equal to C naught. So this is how the equilibrium structure will develop. On the other hand, in the non-equilibrium structures, now non-equilibrium cooling happens because the cooling rate is not slow enough. Because of that, the solute partitioning in the solid state is not complete. As a result, the solid which forms earlier is richer in solute as compared to the solid which forms later. So as a result, the microstructure that you form is, so I am not going to draw all the microstructure, but the microstructure that you form in the material. So you have this initial chunks which are followed by chunks which are formed at a later stage, and then you have another and then the next one, so this is just schematic. Okay, so what this depicts is that you have compositional gradients. So you have compositional gradients in solid phase, which have to be removed by a solutionizing or homogenization treatment after the solid is formed. Now this is something which happens in most alloys because the cooling rates are fast. As a result, solid state diffusion being slower cannot lead to complete homogenization of the solid during the solidification itself. So as a result, extra homogenization step is needed to homogenize the solid. So these are two microstructures that we looked at in alloys. What we were finally looking at was phase evolution in a eutectic phase diagram. So you have a eutectic phase diagram like this. Okay. So you have liquid plus alpha, alpha, alpha plus beta, liquid plus beta, and beta phase. So what we want to understand here is, so this is the composition Ce, this is the composition C alpha E, this is the composition C beta at the eutectic temperature. So this is Te, this is Tmb, if it is B, this is A, this is Tma, and these are the solid solubilities of alpha and beta at eutectic temperature, and these are the solid solubilities of alpha and beta at room temperature, C alpha and C beta at room temperature or at lower temperature. Now, we want to understand the evolution of microstructure in such a solid at various composition. So, for example, this could be the first composition, this could be the second composition, this could be the third composition, and this could be the fourth composition. The evolution of microstructure on the other side will be similar to what happens on the left side. It's just that the phases are different. So, as you know, in the eutectic phase diagram, this region is called as hypoeutectic. Hypoeutectic are the compositions which are lower than the eutectic composition. So, basically C less than Ce, and this region is called as hypereutectic, where C is greater than Ce, and the one which is at the center is called as eutectic composition. So, we first looked at the scenario 1. So, in case of case 1, when C composition of the alloy is lower than the C alpha, which is this point. So, at this point what happens is that the alloy goes from liquid state to liquid plus alpha. So, at this point it is liquid, then it converts into liquid plus alpha. So, this is A, this is B, and finally at C it is 100% alpha at C. So, liquid composition at this point is same as let us say C1. At this point you can draw the tie line. So, you will have composition of liquid as ClB, and composition of alpha will be C alpha B, which is, so this is C alpha B, and this point will, sorry, this will be ClB, this will be C alpha B. So, this is the tie line that you draw, and finally when you come to 100% C point, 100% alpha, then what you have is composition is same as C1. So, this is how the microstructure evolved. So, the microstructure went, if I go to previous lecture, let me just open the so the microstructure went from 100% liquid to some B at point B, and B's composition is different, which, and this alpha is called as primary alpha, eutectic alpha, and before this alpha is nearly formed with very little amount of liquid, and when you are past the solidus line, then it is 100% alpha of composition C1. Okay. So, this is how we did the microstructure evolution. When we finished, we were at this point looking at microstructure of an alloy whose composition is higher than the solid solubility of B in A at room temperature. So, we will close this and we will go to. So, this is what we will do now. So, case 2 is for alloy of composition C2, and what is C2? This is C2. So, this is C2. So, C2 is an alloy whose composition is higher than C alpha, but lower than C alpha E. So, which is, so C2 is higher than C alpha, which is at low temperature or room temperature in many cases, but lower than C alpha at eutectic temperature. So, that is the condition. So, the phase diagram looks like, so I will just bloat the phase diagram, I will not draw completely. So, this is percentage B, this is temperature. So this is the eutectic line, and this is what the scenario is. Okay, and we are following an alloy whose composition is this. So this is C2, this is C alpha, this is C alpha E. Okay, so this is liquid plus alpha, this is alpha, and here you have alpha plus beta. So what will happen here is that now let's take the point A. So at A, microstructure will consist of %. Let me draw a little small circles, otherwise we will not be able to draw all of them here. So at A, it is 100% liquid and whose composition is same as C2. Let us go to point B, which is point B. Point B is just below the liquidus. So point B, what you will have is, you will have liquid mostly with some solid forming. So solid will be present. So these chunks of small pieces of solid which could be regular in shape. So this is alpha and this is pro-eutectic or primary alpha. Okay, so this is primary alpha. Pro-eutectic is generally which is above the eutectic line. So in most cases we call this as primary alpha. Okay, so this is primary alpha, and composition of this can be determined by tie line, and this is liquid. When you come to point C, so I will not discuss the complete solidification through this line. So when we come to point C, so as a home exercise, what you can do is that apply tie line and lever rule in two phase regions to determine the phase compositions and their fractions. So at C, so this is for composition and phase fraction determination. Okay. So at point C, what we have is, we will have, so this alpha would have grown into bigger pieces and finally the liquid is completely solidified. So what you will have is, you will have these chunks of alpha. So this is alpha. See the grains of alpha which are separated by grain boundaries. So these are grain boundaries, and the overall composition of alloy is same as C2. Composition is same as C2. Now what happens is that when you come to point D here, what happens is that as you come into the solid region and as you keep decreasing the temperature, the solid solubility of B in A decreases gradually. So this line is Solver's line that shows that solid solubility of B in A gradually decreases, which means at this point, the moment alpha crosses this particular point, and this is the crossover point, it starts losing, it starts expelling B out of it, and that B precipitates in the form of beta phase, because if you look at the phase diagram on the right side, you have beta phase. So if you look at this point, so we are looking at this point, so if you draw a tie line at this point, so what you have is alpha and beta phase equilibrium. This is the composition of C alpha at whatever D, and this is the composition of C beta at this particular point. So, what happens here is you have this alpha phase, the grains of alpha, okay. So, you have these grains of alpha, and within these grains of alpha you have formation of some beta phase. So, beta phase gets precipitated in the form of small precipitates. So, small crystals of beta will be forming here and there. So, this will be beta phase, and beta phase composition is given by the tie line which intersects at some point. So, composition is C beta D, and the composition of alpha is changed to C beta D, C alpha D, sorry, which is lower than C2. Okay. So, basically an alloy of composition C2 is a mixture of alpha of composition C alpha D plus beta of composition C beta D. The phase fractions can be formed by similar manner. So, when you apply lever rule, so phase fractions at D you will have percentage alpha will be equal to C beta D minus C2 divided by C beta D minus C alpha D into 100, and percentage beta will be equal to 100 minus percentage alpha, which is equal to C2 minus C alpha D divided by C beta D minus C alpha D. So, as you can see that as temperature decreases further below D, you can see that C alpha D decreases further, and hence percentage alpha decreases and percentage beta increases, but the microstructure remains nearly the same. However, so you will have these precipitates of beta formed in the matrix of alpha. So, alpha is the major phase because the composition is hypoeutectic. So, alpha is the major phase with tiny precipitates of beta present within the grains of alpha. So, this is how the microstructure of an alloy of composition C2, which lies between the solid solubilities of B in A at eutectic temperature and at low temperature. So, so within the solid state itself, at point C, it is 100% alpha when you are in the only alpha region, but as you decrease the temperature, the solid solubility of B in A goes down, which means also alpha becomes leaner or thinner in B, and as a result the composition of alpha becomes more A rich and it loses B out in the form of beta, and hence at point D you form a mixture of alpha and beta, which in which proportion of alpha increases, proportion of beta increases as you decrease the temperature further. So, this is how the microstructure will form in case of C2 composition. Now, let us look at microstructure evolution in case of C3. So, again, so this is case 3, alloy of composition C3, and let me define what C3 is. This is C3. Okay. So if I again draw the zoomed in part of the phase diagram, okay. So we are standing at about this point. This is C3 composition, and we have the phase fields liquid, liquid plus alpha, alpha and liquid plus alpha plus beta. Okay. Now again let's look at point A. At A you have 100% liquid of composition C3, which is same as before. At B, at this point, alpha begins to form. So at B, so this is point B, the composition is C alpha, C liquid B, this is liquid, and at this point is C alpha B. By the way, this is temperature axis. So alpha begins to form. So alpha of composition C alpha B is in equilibrium with liquid of composition C liquid B, and you can find the fractions using the lever rule. And this alpha, so the microstructure will be same. So as if you reach point C, for instance, so this is point C, the alpha will increase in quantity and liquid will decrease until we reach point D. So at C, alpha increases in proportion and its composition changes, which you can determine using tie line rule. The moment you reach point D, so I will not draw the microstructure at ABC because you are conversant with them. So, and you can determine their composition and phase fractions using tie line and lever rule. When you reach point D, which is just above the eutectic, okay. So TD is basically TE plus, okay, maybe a few degrees above eutectic temperature. So at this point, what you have is alpha of composition nearly C alpha E, which is this point, and liquid of composition CE. So alpha of composition and C alpha E and liquid of composition CE, these are in equilibrium. And the moment you go below this point, the moment you go to point E, so basically what you will have at this point is you will have basically alpha so this is so this is alpha of composition C alpha E, and very little liquid is left of composition CE just above the eutectic temperature. So you can determine the phase fraction of, and this alpha is called as pro eutectic alpha, okay. So this alpha which begins to form is called as pro eutectic alpha or primary alpha. Now when you reach point E, this alpha remains as it is, but the liquid undergoes this eutectic reaction and it converts into a mixture of alpha and beta. So, the microstructure looks something like this. So, you had this alpha grains. So, I will try to draw the nearly similar one. So, you have these alpha grains. Let me try to draw them absolutely dark. So, these are alpha grains which are absolutely dark phase, gray phase. I am making it absolutely gray because the eutectic feature is slightly different and it looks like so this is alpha. So, alpha will be so this is the pro-eutectic alpha of composition C alpha E, and the liquid converts into a mixture of alpha and beta. So, this appears as this eutectic mixture which is of the form of platelets. So, you will have these platelets of alpha and beta. So, the platelets will appear as if you have these gray and red plates. So, it's like parallel plates of alpha and beta growing together. So, if you microscopically look at it, if you zoom it up, so basically what you have is, so before we zoom it up, so this is basically mixture of alpha plus beta. So, eventual microstructure at point E is alpha which is pro-eutectic plus alpha plus beta which is eutectic mixture. Now, phase wise both the alphas are same, both are similar phases. This alpha is same as this alpha. It is just that the morphology of this alpha, the appearance of this alpha is different from appearance of alpha which is present in the eutectic. So, in the eutectic, so within the eutectic phase, eutectic is well not a phase, it is a mixture. Within the eutectic mixture, you have these parallel plates of and this is alpha. Let me just draw it again. Little. So, these are parallel plates of alpha and beta. So, red one is beta here and the gray one is alpha. So, eutectic mixture is basically colony or set of parallel features, which is called as lamellas. So these are alpha and beta lamellas which grow parallel to each other. So if you look at the mixture of if you look at the microstructure of proeuteric composition, you have this phase which is alpha phase, which is present like this. Okay, so and between these regions of alpha, just kidding. And between these you have these plates of alpha and beta. Growing parallelly. So this is one they can grow in different orientations. So this alpha and beta could be like this. Similarly here. So this is what is basically the eutectic, and this is what is the alpha phase. So I'll come to some more details about this eutectic transformation in the next lecture. But what we have done in this lecture is to look at the phase evolution in a eutectic phase diagram in the hypoeutectic region of 3 compositions. Thank you.